Today I'm going to talk about how to find the LCM, the least common multiple. Suppose I were to ask you, what's the least common multiple or LCM of 6 and 8? I'm sure a whole bunch of you know the answer, right? You would say the answer is 24. And yes, you're right. But then if I were to say, what is the LCM of 35 and 49? Uh, Quite possibly you'll have a little trouble. At least you won't be able to figure it out in your head that quickly. Or if I make the problem a little more complicated, what's the LCM of something like this? 35a square b to the negative 4 times the quantity x minus 2 raised to 5 and all of this, boy, you're in trouble. So the question is there a nice systematic procedure of finding the LCM? And that's what I'll talk about, okay? So let's go back to that simple problem 6 and 8. For if you want to find that LCM of 6 and 8, you write down 6 and 8 and an L bracket, enclose that in sort of an L bracket like that. And then you ask this question, is there an integer not equal to 1 that goes into 6 and 8? Well, because we are dealing with positive numbers, let's say a positive integer that goes into 6 and 8, and the integer, positive integer should not be 1. I'm sure one look at it, you could tell 2 goes into both 6 and 8. So go ahead and write down that 2 to the left of that L. And then ask, okay, 2 goes into 6 how many times? And 2 goes into 8 how many times? 2 goes into 6 3 times and into 8 4 times. So you just write down 3, 4. And then you ask the same question that you did before, which is there a positive integer other than 1 that goes into both 3 and 4? The answer is no. Only 1 goes into both 3 and 4, nothing else. So at that stage, you just take all the outside numbers. What do I mean by outside numbers? Outside that L, there's a 2, 3, and a 4 on the outside. Take all of those and multiply them out, and you got the LCM. As simple as that. 2 times 3 times 4 is 24, and the LCM of 6 and 8 is 24. Okay. Now, let's look at the LCM of 8 and 12. This is not very different from the previous one, I agree, but there's some little concept that I wanted to show you. Okay, we write 8 and 12 as before, put an L bracket, enclose it in an L bracket, and then ask what's a positive integer that goes into both 8 and 12? I'm sure some of you saw that 4 goes into 8 and 12. But let's say you couldn't figure out a big number like 4 going into both 8 and 12. Instead, all you saw was 2 goes into 8 and 12. Well, go ahead. No big deal. Just write down 2 and carry on the division. 2 goes into 8 4 times and 2 goes into 12 6 times. So 4 and 6. Now you ask again, is there a positive integer that goes into 4 and 6 other than 1? Well, 2 goes into both 4 and 6. So extend that L bracket again and write down another 2 and carry on the division. So you get 2 and 3. Is there anything now that goes into both 2 and 3? Nope. So at that stage, you stop and multiply out all the outside numbers, which means in this case, 2, 2, 2, and 3 are the outside numbers. Multiply them out, and you get the LCM 24. Okay. So 35 and 49. Is there anything that goes into 35 and 49? If you're good at your number tables, the multiplication tables, then you recognize 7 does. 7 goes 5 times, 7 goes 7 times. Nothing else goes into 5 and 7, so the LCM is 7 times 5 times 7. End of the story, 245. See how simple it became? The big question is, can you figure out what number goes into both of them? That's the big one. Okay. And now let's extend this concept to algebraic expressions. For instance, what's the least common multiple of a to the m and a to the n? So a is the base, m and n are exponents. Since the base is the same for both the expressions, the LCM turns out to be the one with a bigger exponent. So that's what I mean by LCM of a to the m, comma a to the n is a to the m, provided m is greater than or equal to n. The bigger exponent is the LCM. I apologize if I'm insulting your intelligence. LCM of a to the 5 and a cube are simply look for the, since the bases are the same, look for the exponent being bigger. So 5 is greater than 3, therefore LCM of a to the 5 and a cube is a to the 5. Simple enough, right? Okay. What's up with something like this? LCM of a to the negative 2b cube and a to the negative 3b. Well, in a case like this, you just separate out the terms in the sense we have in one term a to the negative 2, and in the other term we have a to the negative 3. Figure out the LCM of just those things. So a to the negative 2 and a to the negative 3. Which one is the bigger exponent? If I say negative 2 is bigger than negative 3, would you agree? Yes, it is, because if you look at the number line, the arrow is pointing to the right, and that arrow has a lot of significance. It shows that numbers going towards right are increasing. All right, which means a number to the right is bigger than a number to the left. If we take that concept, a number to the right is bigger than a number to the left, would you agree that negative 2 is to the right of negative 3? Therefore, negative 2 is bigger than negative 3. And so, LCM of a to the negative 2 and a to the negative 3, just that alone, is a to the negative 2. But then we have b cube and b. B is nothing but b to the 1. Would you agree? So 3 is greater than 1. So the LCM actually turns out to be a to the negative 2, b cube. You see, just do for the individual ones, figure out the LCM for individual bases if they are equal, and multiply out. As simple as that. In that regard, LCM of this big long thing that I had asked you, well, that appeared to be very complicated in the beginning, but now I'm sure you see that it's not really that complicated. So let's work on it. We see numbers 35 and 49. Did we already go through that LCM of 35 and 49? We found that to be 245, 245. Then a square a to the negative 2. You agree a square because 2 is greater than negative 2? B to the negative 4 b cube, obviously b cube. X minus 2 to the quantity 5, x minus 2 to the negative 1, so x minus 2 to the 5. So there you go. So that is the LCM of that big long stuff. That's all there is to this one. Okay.